In 2021, a radioactive reservoir in Manatee County was on the edge of collapsing. The reservoir sat on top of a mountain of radioactive fertilizer waste called a phosphogypsum stack, holding almost 400 million gallons of contaminated water. Officials evacuated hundreds of nearby homes and dumped water into Tampa Bay just to keep the wall from failing completely. That stack is one of more than 24 like it across Florida, sitting on the same ground that feeds the state's drinking water. This is the story of how that structure got built, what happened in 2021, and why the rules that govern it look nothing like the rules for a nuclear plant. Florida has 2 nuclear plants, and most people can place them without much trouble. Turkey Point sits near Miami and has been running since the early 1970s. St. Lucie sits near Port St. Lucie and came online a few years after that, and both are owned and operated by Florida Power and Light. Both recently had their federal operating licenses renewed for another 20 years. That means both just went through the kind of hearings, inspections, and public dockets that a reactor goes through on a regular schedule. That's not what this video is about. Southwest of Tampa is a region called Bone Valley. It's been the center of Florida's phosphate industry since prospectors first found thick beds of phosphate rock there in the 1880s, buried under just 20 to 50 feet of sand and clay. That shallow overburden is the whole reason the industry grew as large as it did. Stripping 20 or 30 feet of sand off the top was cheap compared to phosphate mining almost anywhere else on Earth. Companies kept stripping it across Polk, Hillsborough, Manatee, and Hardy counties for well over a century. Turning that rock into usable fertilizer means dissolving it in sulfuric acid. One stream comes out as phosphoric acid, and that becomes the fertilizer that ends up on farms. The other stream is a leftover mineral slurry, mostly calcium sulfate, called phosphogypsum. Instead of getting sold or shipped anywhere, it gets pumped up and stacked into mounds that can rise more than 200 feet into the Florida sky. Florida's own environmental regulators count roughly 25 of these stacks scattered across the state today. Every one of them sits on karst limestone, a soft, porous rock riddled with cracks and hollows. That limestone holds the Floridan aquifer underneath it, the same aquifer that supplies most of Florida's drinking water. A reactor gets built behind fences, inspectors, and decades of engineering review. A gyp stack gets built on ground that can open up without warning. That's the setup. Now here's what's actually inside these mountains, and why the waste stream is where this story gets interesting. Phosphate rock naturally carries trace amounts of uranium and radium left over from the same slow decay chains that run through the Earth's crust everywhere. Those are the same chains that leave a little bit of natural radioactivity in granite countertops and backyard soil. On its own, that's not unusual. Most rock on the planet carries some background radioactivity, and in most settings, it rarely amounts to much of anything. Before any of that rock reaches an acid plant, it goes through a beneficiation plant first. Drag lines and washing equipment strip out sand and clay there, leaving behind a concentrated phosphate ore ready for processing. That step alone has run continuously across Bone Valley for well over 100 years. It feeds a chain of fertilizer complexes built specifically to turn Florida rock into a product that gets shipped to farms across the country and overseas. What makes Bone Valley's phosphate rock different is what happens to it inside the acid plant. Sulfuric acid dissolves the rock and splits it into 2 separate streams, but the split isn't even. The phosphorus that goes on to become fertilizer comes out comparatively clean, while the uranium and radium concentrate hard into the calcium sulfate waste left behind, the phosphogypsum. Regulators who study this process have found that the leftover waste can end up more radioactive than the rock it was pulled from. That happens simply because of where the chemistry sends each element. Nothing about the acid itself is exotic or secret, since sulfuric acid dissolving phosphate rock is standard industrial chemistry used at fertilizer plants around the world. What's specific to Florida is the sheer volume running through that chemistry, year after year, on top of ore that happened to carry more uranium and radium than most. This isn't a leak, a spill, or an accident anybody needs to explain away. It's the designed output of a chemical process that's been running continuously in Florida since the 1880s. That's a scale that's genuinely hard to picture standing on the ground next to it. Each ton of phosphoric acid produced leaves behind several tons of phosphogypsum. Multiplied across more than a century of continuous Florida phosphate mining, that adds up to tens of millions of tons sitting in stacks across the state right now. Here's the part worth sitting with for a second. The fertilizer bag that ends up on a shelf at a garden center has nothing radioactive in it at all. The radioactivity wasn't hidden, misplaced, or lost track of somewhere in the process. It was engineered out of the product on purpose, routed instead into a 200-foot mountain of leftover mineral waste, sitting a few miles from the plant that made it. That's not a flaw in the process. That's the process designed to work exactly as it was designed to work, decade after decade, on an industrial scale nobody pictures when they pick up a bag of fertilizer. Think of it less like a spill and more like straining coffee grounds out of a pot. Nothing goes missing. It just ends up sorted into two very different piles, and one of those piles happens to keep the radioactivity. It also raises the obvious next question, the one this video turns to next. Here's what's actually sitting inside that mountain, element by element. The two elements that matter most here are uranium, 238, and radium 226, along with the chain of decay products they keep producing over time. Radium 226 is a bone-seeking alpha emitter with a half-life of about 1,600 years. That means a gyp stack built today will still be generating radioactive decay products long after everyone alive right now is gone, and it will keep generating them long after anyone remembers who mined the rock that made it. One of those decay products is radon 222, a gas, and gas is what regulators actually spend their attention on. Unlike the solid material sitting in the stack, radon can move through cracks and pores and drift straight into the open air above it. Outdoors, at low levels, it disperses and isn't much of a concern. Breathed in at higher concentrations over a long period, especially indoors, it's a documented cause of lung cancer. Federal estimates put the added lifetime cancer risk from a year of elevated indoor radon exposure at somewhere around 6 extra cases for every 100,000 people exposed. It's worth putting that half-life next to uranium 238, which runs into the billions of years, practically forever on any human timescale. Radium 226 is the faster-moving link in that same chain, the one that actually produces the radon gas people breathe. Researchers who've studied stacks like these have found genuinely mixed results, depending on how well a given site is managed. One study of a phosphogypsum stockpile found its radiological impact on the surrounding area was fairly minor under normal, well-maintained conditions. A separate study measuring phosphogypsum in a different country found radionuclide concentrations that exceeded the recommended safety limits for direct use. The honest answer is that it depends heavily on how the stack is built, sealed, and watched, which is exactly why the watching part matters so much. The federal rule built specifically around this is EPA's Subpart R, and it's narrower than the name suggests. It sets a radon flux limit for inactive stacks, capping how much radon can escape per square meter of surface each second. It separately caps the radium concentration allowed in any phosphogypsum distributed for use in agriculture. If a stack's emissions creep above that flux limit, the fix is a retest within 90 days, and then just once a year after that if the numbers come back clean. The EPA also blocks phosphogypsum from most other uses entirely, including road construction, specifically because of these same radiological concerns, allowing only narrow, tightly limited exceptions for agriculture and research. Picture the kind of radon test kit a homeowner might set in a basement for a few days out of general caution. Multiply that basic level of attention across a 200-foot structure covering acres of ground, tested once a year under ordinary conditions, and that's roughly the scale of routine attention involved. No detonation risk here, no glow in the dark, nothing that dramatic or cinematic about it. The real danger runs slower and quieter, a centuries-long gas seep from the surface, plus a groundwater problem if the structure underneath the stack ever gives way. As it turns out, that second scenario isn't hypothetical. It's already happened, more than once. In 2016, a sinkhole opened underneath a Mosaic Company gyp stack near Mulberry, and the ground simply dropped away beneath it without warning. Roughly 215 million gallons of acidic, contaminated water drained straight down through that opening into the Floridan aquifer, the same aquifer that supplies drinking water across the region. Karst limestone does exactly that under the right conditions, collapsing suddenly with almost no advance sign directly underneath a structure engineered to hold hundreds of millions of gallons of waste. Exactly how long that particular sinkhole had been quietly leaking before anyone caught it is not fully settled in public reporting. The leak itself, and the volume that reached the aquifer, was confirmed by the company and by state officials. 5 years later, a different kind of failure hit Piney Point, an older phosphate site in Manatee County that had already stopped active mining. It had been left behind with a wastewater reservoir sitting on top of its own gyp stack. A liner gave way, and the reservoir wall came close to a full structural collapse. Officials called it an imminent failure and evacuated hundreds of nearby homes as the water level kept climbing toward the breaking point. To relieve the pressure before the wall failed outright, crews deliberately released contaminated water into Tampa Bay over roughly 10 days. One estimate put the discharge at close to a year's worth of hazardous nutrients entering the bay inside that single window. Even after that release, more than 250 million gallons of wastewater still remained sitting in the stack. The fear driving the whole evacuation was straightforward: a wall of contaminated water breaking loose all at once into the neighborhoods sitting downhill from it. These aren't two unrelated freak accidents that happen to hit the same industry. They're the two different ways this exact kind of structure fails: down into the aquifer or out into surface water. Both trace straight back to building a stack this large on top of Florida's specific geology. Peer-reviewed modeling of the Mosaic leak estimated it could take somewhere between roughly a decade and nearly 2 decades for contaminant levels in that stretch of aquifer to naturally fall back to the drinking water threshold. How long exactly depends on how much the surrounding rock and minerals slow the plume down. A separate estimate that accounts for those minerals actively absorbing some of the contamination puts the recovery window a little lower, closer to 9 to 16 years. Piney Point still isn't finished closing, years after the emergency made national news. As of early 2025, only one section of the stack had been capped with a liner and grassed over, with a second section just beginning the same process. The state had committed around $185 million toward finishing the job. Florida's Department of Environmental Protection now keeps a standing web page dedicated just to Piney Point, tracking the closure work section by section. That alone is a sign of how much ongoing attention one failed reservoir still demands years later. This is a live engineering problem still being worked through in real time, not a settled one you'd only find in the history books. After 2 failures at this scale, on ground this sensitive, the obvious question is, who's making sure it doesn't happen a 3rd time? That's where the story turns strange. 2 separate decisions, made decades apart, are the reason a gyp stack answers to almost nobody. The first came in 1980, when Congress carved a broad category of mining and mineral processing waste out of hazardous waste law entirely. It filed that category under a temporary label called special waste, while further study got done. That category wasn't written for phosphogypsum specifically. It also covers red mud left over from refining bauxite into aluminum, and slag left over from smelting metal and phosphorus. All of it got lumped together as high-volume byproducts, presumed to carry lower hazard than they might actually deserve. That study ran for over a decade, and in 1991, the EPA finished it and made the exclusion permanent, naming phosphogypsum specifically alongside that same short list of mining byproducts. It has never been reversed since. Phosphogypsum simply turned out to be one of the biggest and most radioactive things sitting inside a category that Congress had built for an entirely different, much broader purpose. The second decision sits in a completely different law written for a completely different purpose. Under the Atomic Energy Act, nuclear byproduct material is defined narrowly as material made radioactive by producing nuclear fuel or waste generated by mining uranium directly out of the ground. Phosphogypsum's radioactivity is naturally occurring in the phosphate rock itself, just concentrated by an acid process that was never built with radiation in mind. Legally, it falls into a separate bucket entirely, one the EPA calls technologically enhanced, naturally occurring radioactive material. The Nuclear Regulatory Commission, the agency that licenses Turkey Point and St. Lucie, has no jurisdiction over any of it. Put those 2 exclusions together, and here's what a gyp stack actually gets, compared to a reactor. A nuclear plant gets a federal license, a continuous on-site inspection presence, and a public enforcement docket that anyone can read. A gyp stack gets 1 federal rule, administered by EPA's air program rather than a dedicated radioactive materials regulator. Place the waste in a stack and keep radon emissions under a ceiling. Retest happens once a year and only if a prior check suggested a problem. That's the entire gap this video has been circling since part 2, and it isn't an oversight anyone missed. It's a deliberate choice EPA has now reaffirmed twice. This isn't settled history either. Environmental groups, including the Center for Biological Diversity and a local group called People for Protecting Peace River, first petitioned the EPA back in 2021. They asked the agency to reverse its 1991 decision and start regulating phosphogypsum as hazardous waste. It took roughly 5 years and a formal notice of intent to sue just to get a response. In April of 2026, the EPA proposed denying that petition outright. Public comment on that proposed denial closed at the end of May 2026, and a related legal settlement now requires the agency to issue a final, binding answer no later than February of 2027. The secret here was never a cover-up. It's a label drawn by 2 statutes written years apart that happens to leave something this large and this close to the water supply sitting on the lighter side of both of them. That exact label is still being argued over in federal filings this year. Lay the 4 pieces next to each other, and the whole picture snaps into focus. Karst geology made these stacks vulnerable to sudden collapse, the kind that opens without warning under hundreds of millions of gallons of waste. The acid process, running since the 1880s, guaranteed that any collapse would carry uranium and radium with it, rather than something inert. A regulatory category written in 1980 and locked in permanently by 1991 guaranteed that almost nobody would be watching closely enough to catch it early. No single piece of that creates the risk by itself. It's the combination of all four: geology, chemistry, industrial scale, and a decades-old legal filing stacked directly on top of each other. Each piece on its own actually sounds reasonable. Karst geology exists all over Florida regardless of what's built on it. A chemical process that concentrates naturally occurring radioactivity into a byproduct stream isn't unique to phosphate mining either. And a regulatory judgment that most mining waste poses lower hazard than something actively toxic is a defensible starting position. It made sense for a 1980s era Congress trying to sort thousands of waste streams at once. It's only when all three land on the same 200 feet of ground, repeated across roughly 25 sites statewide, that the combination stops looking reasonable. That's when it starts looking like something worth watching closely. Go back to the reactor comparison from the start of this video because it holds up better than it might seem to on the surface. A reactor is small, contained, and built under a licensing system, specifically designed to withstand the kind of failure a gypstack has already had twice in the last decade. A gypstack, by contrast, is a far larger, far older structure holding comparable long-lived radioactive material, monitored by a fraction of the oversight a reactor gets. It sits on ground that's already proven twice over that it can open up underneath one. The 2016 and 2021 incidents weren't just bad luck meeting bad timing. They're what happens when a structure gets engineered for a lower risk regulatory tier and then gets built directly on top of geology that never agreed to stay low risk. The paperwork from 1980 and 1991 assumed a smaller consequence than karst limestone was always going to deliver eventually, and Bone Valley delivered it twice within 5 years of each other. That Manatee County reservoir from the very beginning of this video is a small, specific window into that same larger pattern. It wasn't a rogue facility cutting corners or ignoring the rules. It was one ordinary gypstack built and regulated exactly the way federal law says a gypstack gets built and regulated, and it still came close to a catastrophic failure. What that failure proves is bigger than one operator having a bad year. It proves what the entire category of structure is legally allowed to be. The EPA is weighing whether to reverse that 1991 exclusion right now, with a legal deadline sitting less than a year out. That means the classification holding this entire system together could genuinely change before this decade is over. This is the live wire still running underneath everything just laid out here: geology, chemistry, and 30-year-old paperwork. All of it is stacked on top of each other in the same 200 feet of ground. If you live in Florida, or you are seriously weighing whether to move there are a few things worth actually doing with everything this video just covered. Florida's Department of Environmental Protection publishes a public geospatial map of every gypstack in the state. It is the same kind of data set you would already check for a flood zone before signing on a house. It takes a few minutes to pull up any address and see exactly how close it sits to one of these stacks. It is public information, not something you have to file a request to see. If you are on a private well anywhere near a phosphate region, it is worth knowing something specific. Municipal water systems run required, published water quality testing that a private well owner simply does not get handed automatically. Nobody is testing that well for you on a schedule the way a city utility gets tested. That gap is worth closing yourself with independent lab testing, particularly for radionuclides. It should not be assumed that the same municipal-grade oversight applies just because the water coming out of the tap looks and tastes the same either way. A private well does not come with the same paperwork trail a public utility is legally required to publish. So the burden of finding out sits with the homeowner rather than any agency checking in automatically. And keep an eye on February of 2027 specifically. That is the legal deadline for the EPA's final decision on whether to reclassify phosphogypsum, the first review since the exclusion was made permanent back in 1991. Whichever way that decision lands, it will be the biggest change to this entire rule in more than 3 decades. It is worth watching now while the comment period and the litigation are both still active, rather than after the decision is already final. None of this is limited to the handful of counties where the stacks physically stand either. The Floridan aquifer does not stop at a county line, it stretches under most of the state. That is the same reason a sinkhole near Mulberry can affect water quality readings well outside Polk County. Living near Bone Valley makes the stakes obvious, but drinking from the same aquifer system is a statewide condition, not a local one. So the plant everyone in Florida can already name isn't the radioactive structure most worth watching. The mountain nobody bothered to name is. If you want stories like this explained before you hear about them secondhand, subscribe to Florida Empire, because Florida keeps building things exactly this deliberate, and most of them never got a warning label either.